Okay, in this data task about classification, we start off with 18-year-old females and a large number, measure the height and the female length. So a couple of things we notice here, which if you got an evaluation question using this resource, we didn't in these questions, but you could have done. A large number, that means it's a representative sample. And we've controlled two variables. We've got 18-year-olds and we've got female, and they allow comparison between the data. And why does it allow comparison? Well, because height and female length could change if they were older, or if they were older or younger, or if they were male or female. So always link a control variable back to how could it affect what you're measuring. Then looking at the data, you can see that with height, we've got a standard deviation, and we've got a range, and the same for female length. So the first question asks, calculate the ratio of height to female length. So height to female, this is how, if you ask a question in an exam, and in biology, we always do it to 1 at the end. So 167.32 to 41.83. We want to get it to 1 on this side, so if you divide both numbers by whatever is on this side, so both sides divided by 41.83, and it gives a 4 to 1 ratio. So the height is 4 times more than the female length. You do sometimes get questions, what's the difference between standard deviation and range? So in this question here, so range. Range is simply the lowest to highest number. So the smallest height in this sample is 150.5, and the tallest girl in this sample was 181 centimetres. Standard deviation shows the spread around the mean. So it's a spread of data around the mean, so that's another mark point. And this shows how distributed the data is. And as you can see in these graphs here, the dotted line representing the mean from the top of the normal distribution curve. A small standard deviation would mean that most of the data is close around the mean, whereas a large standard deviation would mean that the data is very spread around the mean. So how do you get the marks for this question? Question 2. First of all, range shows from lowest to highest, but the range is affected by outliers. So there might have only been one person with this height or one person with that height. The standard deviation shows the spread around the mean. So it's showing you where most of the data is found in the population. And range does not show how the data is distributed. So that would be the 3 marks you could get for that. Okay, in this question, evaluate Australopithecus looks similar to modern humans. There's not really any yes points you can have for this. So there's nothing to indicate that that's the case. So what things go against that they look similar to modern humans? Well, first of all, the sample size is very, very small, so it's not representative at all. Other things we could have had is the female length is smaller, so that means that they're likely to have been shorter. Also, linking to the previous resource that we did, there might not, as we don't have any indication of height, the ratio might have been different. So they might have had a larger femur compared to total height, or the opposite way around. So we don't have any idea of the ratio between height and femur length either. And the other thing is as well, we stand upright, Australopithecus might not. Okay, the next set of data is looking at whether altitude affects sort of body size, body mass. You can see that we've tried to make control groups out of this, so we've used a similar age, because age could affect body mass, and we've looked at the same, so all males, so again, that could affect body mass, male, female, could affect body mass as well. So, it tells you in here as well that higher altitudes are colder, so you need that bit of information to link to the question. The question was, heavy people are adapted to live at lower altitudes. So, looking at this we can say yes, because they've got the highest body mass at lowest altitude, so the highest body mass at the lowest altitude. there's no standard deviation bars overlap between here and here, so showing that there is a significant difference between 3,500 metres and 100 metres. So significantly higher body mass at 100 metres compared to 3,500. But then there's a lot of no points as well for this evaluation. There is not a significant difference between 2,500 metres and 100 metres because the standard deviation bars overlap. There's no statistical test used. So between these two means you could have done a t-test, between these two means you could have done a t-test, between this mean and this mean you could have done a t-test, to prove to what level of probability the difference is due to chance. And the other thing as well, there's no sample size on here. We don't know if the results are representative. The last task just asks what conclusions can you take from the data that we've got. Okay, so we're looking at two things that can affect diabetes. We've got age and we've got mass. So what can we see? So hopefully you can see as you go from the younger to the older age group, each of the bars increases. So with diabetes, more people have diabetes for all age groups as they get older. Also you can see that in the younger people, the percentage that are diabetic is much higher with the obese group. Older age and normal, so older age, normal overweight have the same diabetic risk, but the highest is still obese. With obese, it is much more likely that you become diabetic at an earlier age, but then as you increase the age, there's not much of an increase with the obese group. There's the biggest proportional increase with normal weight as you increase with age. So if we're going from here to there, the percentage of women with diabetes doubles.